Hello YouTube, how's it going? DAT Simplified here. Today we're going to be talking about quantum numbers and what you need to know about them for your upcoming DAT. So let's get started. So regarding quantum numbers, there are four basic quantum numbers that you need to know for your DAT, and they are as follows. The first one is going to be your n, and that is the basic quantum number. That's basically equivalent to what row you're in. So this is row 1, this would be n equals 1. This is row 2, this would be n equals 2. This is row 3, n equals 3, and so on. So this number is the distance from nucleus. Of course, as this increases, the distance increases from the nucleus, and the electrons are actually going to be more negative because they're further away from the positive charge, so their negative charge is going to be less hindered. I should say less cancelled by the positive charge. Anyways, out of the scope of this video, so n is the distance from the nucleus. The second quantum number that we need to know is L, and that tells you the subshell type. This is usually n minus 1. You just get your n number and you subtract by 1 and you get L. However, you have to take this equation with a grain of salt. It only works with certain n numbers, and you're gonna see here in a second. So L can either be 0, can either be 1, either be 2, or either be 3. When L is 0, that means it's S. When L is 1, that means it's P subshell. When L is 2, that means it's D subshell. And when L is 3, that means it's F. And we already know the S can only take 2 electrons. The P can take 6 electrons, hence it has 6 boxes in it. Each box can take 2 electrons, so 6. The D can take 10 electrons, so it has 5 boxes in it. And then finally the F can take 14 electrons, so it has 7 boxes in it. 1, 2, 3, 4, 5, 6, 7. Okay, so this is this. Notice how we stop at 3. L can never ever be higher than 3. Let's say you got n equals 6 and you applied this equation, 6 minus 1. Theoretically it would be L equals 5, but like we said here, L can never be 5. The highest it can be is 3 because we don't have a letter after F. So anything, whenever you see in a question L equals 4, 5, 6, anything higher than 3, it's immediately wrong. That doesn't make any sense. So L stops at 3, no matter what. Okay, moving on. Now we have our ML number, and that's telling you the specific orbital. Specific orbital. This number is the range. You get this number after you look at your L number, and it is the range values of the L number. So what am I talking about here? Let's say we deduced that our L was, let's say, 3. So we know it's going to be an F subshell. So when we draw this, 1, 2, 3, 4, 5, 6, 7. So ML is going to be the range of this. So it's going to be -3, -2. It can be -1, could be 0, could be 1, could be 2, and it could be 3. And notice how it perfectly lines up with the 7 boxes that we have here. This you can say this is the -3 box, this is the -2 box, this is the -1 box, this is the 0 box, this is 1, this is 2, this is 3. So yeah, ML is basically the range of the L from -3 to +3L. And finally we have the last quantum number, which is pretty straightforward. It's just the electron spin. It's almost always either +½ +1/2, or -1/2. And there's nothing much that you need to know about this number. Alright, so let's say you're given something like this and they are asking you to find the specific area the electron is, the specific address of the electron. So from this information, we can actually know a lot about the element or about the electron configuration. When n equals 4, that means we're in the fourth row. So it's probably going to be, this is 1, 2, 3, 4. So it's probably going to be one of these elements. And so it's going to be fourth row. L equals 1. We know it's going to be in the P, it's going to be a P subshell. So this is a huge, this tells us a lot. So it's going to be in this area. This is the P area. This is the D. I didn't mention that in the video. So this is the P area. These are the D. This is the S. And then here you have the F. These two rows are F. And so we know this is going to be in the P subshell, and ML is -1. So let's say we're trying to find where the valence electron is going to be. So we know the P subshell is going to be, can take 6 electrons, so it's going to have 3 boxes. And this would be the -1 box, this would be the 0 box, and then this would be the 1 box. So ML is -1, so our electron of interest is going to be in this box here. So it's going to be either this one, or we won't know specifically which one, whether it's the one facing up or whether it's the one facing down, but we were able to narrow it down. So we were able to determine that the electron is in the -1 subshell, in the -1 orbital of the P subshell of the fourth level. And now I'm going to talk about some common DAT questions that they love to ask you on any test. Basically what they are, they will bring you, they will give you a set of 5 options, and you have to determine which of these options is possible, or which of these options is literally not possible, is literally not a possible set of quantum numbers. Let me show you what I'm talking about. Okay, so let's say you got a question like this on your DAT, and you need to determine which one of these 4 options is a set of quantum numbers that makes sense. So let's look at option A. We have n equals 5, L equals 4, and ML equals -1. Previously, we already said that L cannot be higher than 3, so we can immediately eliminate option A, because 4 does not tell us, there's nothing higher than L. If L equals 3, that means it's F, and there's nothing higher than F, so L equals 4, that doesn't make any sense. Option B, we have n equals 3, okay, that's fine. L equals 3. That's a quantum, that's possible. L equals 3, and ML equals 0. However, since n equals 3, this is where the n-1 rule comes in. L has to be always 1 lower than, well, not necessarily 1 lower, but it cannot be equal to n. It has to be smaller than n. So in this option, since L is 3, it's wrong. It can the possible values for L in this option are either 2 or 1 or 0. So this would be wrong. Let's look at option C. Okay, n equals 4, L equals 3. So here we have this agreement here. This is fine. But notice how ML is 4, and we already said that ML is the range of this. So you can have your ML could be either -3, -2, -1, 0, 1, 2, 3. It cannot be either 4 or -4. So this is wrong because it's out of the range of the L. And finally, we're left with option D, which is n equals 2. Okay, L equals 0. That's fine. And then ML equals 0. So this is pretty. This is a possible set of quantum numbers. Notice how, yes, and the L here is not n-1, but it's still possible. If you look at it, if you look at the periodic table here, you go to the second row. This is the S area, as we said earlier, and then this is the P area. Since n equals 2, we're in the second row. You can have an S orbital, or S subshell, I'm sorry, or a P subshell in the second level. So L here can either be 0 or 1. And since it's 0, we're good. ML here is 0, we're also good. So option D is the one that makes sense. And yeah, that's all I have to say for about quantum numbers. If you guys have any questions, please leave them down in the comments below. I'll be more than happy to answer them. And best of luck studying for your DAT. Have a great day or night, and I'll see you guys soon. Goodbye.